Most people picture Earth vaporizing instantly in a wall of fire, but the physics tells a more precise and stranger story. You'd have exactly 8 minutes and 20 seconds of complete normalcy before a 10,000 kilometer per second shockwave made that the least of Earth's problems. The Sun contains 99.86% of all mass in our solar system, a thermonuclear furnace converting 600 million tons of hydrogen into helium every single second. If that engine catastrophically failed tomorrow, the shockwave would reshape the entire solar system in hours. But here's the twist. Real physics says this scenario is genuinely impossible, and the reason why reveals something extraordinary about how stars actually live and die. Light travels at 299,792 kilometers per second, which means the Sun's explosion would be invisible to us for exactly 8 minutes and 20 seconds, the time it takes photons to cross the 150 million kilometer gulf between us and our star. During those final peaceful minutes, you'd drink your coffee, check your phone, completely unaware that the source of all life on Earth had just detonated. Then the sky would ignite. A wall of radiation, X-rays, gamma rays, ultraviolet, would slam into the upper atmosphere at light speed. The ozone layer would be stripped away in seconds. Surface temperatures would spike by thousands of degrees almost instantaneously. Every satellite in orbit would be fried. The International Space Station, orbiting at just 408 kilometers altitude, would be engulfed in a plasma wave. In this hypothetical apocalypse, the light itself is the first killer. Minutes after the radiation front, the real devastation arrives. A supernova-scale explosion releases roughly 10 to the 44th joules of energy. That's more energy in a single second than the Sun would normally emit across its entire 10 billion-year lifespan. The expanding shell of superheated plasma, traveling at roughly 10,000 kilometers per second, would reach Earth's orbit in about 4 hours. When it strikes, our planet's magnetic field, which normally deflects solar wind, would collapse like tissue paper in a hurricane. The atmosphere would be physically stripped from the planet, blasted into space within minutes. The oceans would boil, then evaporate entirely. Earth's rocky surface would be heated to incandescence, eventually melting into a molten sphere. Our planet wouldn't just be destroyed, it would be effectively sterilized down to the mantle. With the Sun's mass suddenly gone, gravity's leash snaps, but not instantly. Gravitational changes also propagate at the speed of light, so for those same 8 minutes and 20 seconds, Earth would continue orbiting a star that no longer exists. Then, untethered, every planet would fly off on a straight-line trajectory tangent to its former orbit. Mars, Jupiter, Saturn, all flung into interstellar space at their orbital velocities. Jupiter, moving at 13.1 kilometers per second, would drift toward the constellation Virgo. Earth, traveling at 29.8 kilometers per second, would sail into the void at roughly 1/10,000th the speed of light. Within a few million years, the former planets of our solar system would be scattered across dozens of light years, lonely rogue worlds wandering the galaxy in permanent darkness. The solar system wouldn't end, it would simply dissolve. Here's where speculation meets reality, and reality is reassuring. The Sun physically cannot explode as a supernova. It doesn't have enough mass. Supernovae require stars with at least 8 solar masses, because only those giants can fuse elements all the way up to iron in their cores, triggering catastrophic gravitational collapse. Our Sun, a modest G-type main sequence star, weighs exactly 1 solar mass, obviously, and will never produce elements heavier than carbon and oxygen in its core. It simply lacks the gravitational pressure to ignite those advanced fusion stages. When astronomers look at the Hertzsprung-Russell diagram, the Sun sits squarely on the main sequence, roughly halfway through its stable hydrogen-burning phase. It has been shining steadily for 4.6 billion years and has approximately 5 billion more to go. There is no mechanism in known physics that could make it detonate tomorrow. Stars don't just explode randomly. They follow precise evolutionary paths dictated by their mass. As we explored when we looked at how black holes form, the most massive stars burn through their fuel in just a few million years, racing toward iron cores that trigger collapse. But mid-range stars between 8 and 20 solar masses end as neutron stars, while those above 20 solar masses can collapse into black holes. Our Sun falls into an entirely different category. In about 5 billion years, it will exhaust the hydrogen in its core, causing the core to contract and heat up while the outer layers expand dramatically. It will swell into a red giant, engulfing Mercury and Venus, with its outer edge possibly reaching Earth's current orbit at roughly 1 astronomical unit. This expansion phase will last approximately 1 billion years, a slow, majestic transformation, not a sudden explosion. After its red giant phase, the Sun will shed its outer layers in a glowing shell of ionized gas called a planetary nebula, one of the most beautiful phenomena in the universe. The Hubble Space Telescope has captured hundreds of these. The Ring Nebula in Lyra, the Cat's Eye Nebula in Draco, each one the ghost of a sun-like star. Left behind will be the Sun's exposed core, a white dwarf roughly the size of Earth but containing about 54% of the Sun's original mass, giving it a density of approximately 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 tons on Earth. This stellar remnant will glow with residual heat for trillions of years, slowly fading from white to yellow to red, and ultimately to a hypothetical black dwarf, an object so cold and dark that none are believed to exist yet in our 13.8 billion-year-old universe. So the Sun won't explode, but it isn't entirely harmless either. Coronal mass ejections, or CMEs, regularly hurl billions of tons of magnetized plasma into space at speeds up to 3,000 kilometers per second. In 1859, the Carrington event, the most powerful geomagnetic storm ever recorded, sent aurora borealis as far south as the Caribbean and caused telegraph systems worldwide to spark and catch fire. A Carrington-scale event today would cause an estimated $1 to $2 trillion in damage to power grids, satellites, and communications infrastructure, with recovery taking 4 to 10 years. NASA's Parker Solar Probe, currently orbiting within 6.1 million kilometers of the Sun's surface, is helping scientists understand these eruptions in unprecedented detail. The Sun won't kill us with an explosion, but it reminds us constantly that living beside a star demands respect and vigilance. The Sun isn't a ticking bomb. It's a middle-aged star, following a script written by gravity and nuclear physics, with 5 billion years of steady light still ahead. But not every star gets such a gentle ending. Next time, we'll trace the entire life cycle of stars, from nebula to neutron star, and discover why mass alone decides whether a star fades quietly or tears itself apart.